Okay, we're ready to start. Welcome everyone, and thanks for joining us today for Neuroelectrics webinar. My name is Rafał Nowak, and I will be your host today. And so this is the 8th of a series of Neuroelectrics webinars. And today we'll be talking about multifocal transcranial burst and noise stimulation for neurological and psychiatric disorders. I'm very happy to welcome our guest speaker, Professor Dirk de Ridder. Dirk is joining our webinar from New Zealand. Good morning, Dirk.
Good morning.
We are happy to have you here, and sorry for waking you up so early in the morning.
No worries.
Just a little housekeeping before we get started. We'll begin with Dirk's presentation with the duration of approximately 45 minutes. And this will be followed by questions and answers period. So please free to submit your questions at any time using the chat tool. And for your information, this webinar will be recorded and available offline. So please let me quickly introduce our speaker, Professor Dirk de Ridder. Dirk is a professor of neurosurgery at Dunedin School of Medicine, the University of Otago in New Zealand. His main clinical interest as a neurosurgeon is microvascular decompression surgery, skull-based surgery, including vestibular schwannomas and pituitary surgery. And his initial research interest was and still is the understanding and treatment of phantom perceptions like sound and pain, especially by use of functional imaging and non-invasive and invasive neuromodulation techniques. His current research interest is to understand commonalities in different diseases such as thalamocortical dysrhythmias, like pain, tinnitus, Parkinson's disease, depression, and slow-wave epilepsy, and reward deficiency syndromes like addiction, OCD, personality disorders. Third pillar of his research related to the neurobiological underpinnings of the self and other in the brain, as it relates to social interactions, philosophy, and religion. He has developed burst and noise stimulation as novel stimulation designs for implants and is working on other stimulation designs, has published close to 40 books, book chapters, co-edited the textbook of Tinnitus, and has authored more than 300 articles. So obviously, a lot of shared interest with us here at Neuroelectrics. Welcome, Dirk. So glad you can be with us today, and I will now hand over the floor to you.
Thank you. Good evening, everybody. So what I will be presenting today is how, from a neurobiological view, we can use multifocal transcranial electrical and magnetic stimulation to treat the commonalities of neurological and psychiatric disease. But if we want to start evaluating how we can apply non-invasive neuromodulation, we have to have a concept of how the brain works, or a background that allows us to treat the brain disorder in a rational way. And so if we just consider the brain as an information processing machine, then we have to look first, what is information? And information is an elusive term. It's neither matter nor energy. It needs matter for embodiment. And so it needs a brain, basically, if we look at it from a brain point of view. And it needs energy for communication, which we can see, for example, if we look at the Bolt signal in fMRI. So going back to Plato and Aristotle, information can be defined in a relatively simple way. It is imposing a form, which is in the word itself, or a pattern onto something. For example, here we see a form of a Dalmatian dog in the background, whereas the rest of the picture is what we would call noise or randomness, which basically means that there is a lack of form or pattern. Now, in order to look at information, we can look at it from an information point of view, or from a thermodynamics point of view. And we all have heard about the word entropy, which is a measure of disorder and basically a lack of structure. And it's interesting that from an information theory point of view, entropy is or can also be conceived of as missing information or a lack of form, a lack of pattern, a lack of structure. Now, when we consider the brain as an information processing machine, we can also conceive of it as a complex adaptive system, just like ant colonies are, or the economy is, or the web is. And these complex adaptive systems actually arise when two conditions are fulfilled. One is that the complex adaptive system has a structure characterized by small world topology, and the second is the presence of noise. So from a simple point of view, the brain can consist of two extreme states. One would, or topologies, one would be a regular or lattice topology, and the other one would be a random topology. The lattice topology means that if you apply a stimulus, you will always get exactly the same response, which of course is not very practical. If you always respond to a stimulus in the same way, that does not make you very adaptive, and therefore will not be selected through natural and sexual selection. A random topology means that if you supply a stimulus to the brain, it will always respond randomly in a different way. And of course, also that is not an optimal situation. And therefore, evolution has favored the development of an intermediate between a regular system and a completely random system, which is the small world topology that you can get, for example, by creating some long distance connections between introduced in a lattice topology. And this is how the brain is formed both structurally and functionally. And also the presence of noise is an essential characteristic of a complex adaptive system. Now, all these complex adaptive systems have the same characteristics. One is that they are complex by definition, just meaning that the brain consists of many parts that are connected in an intricate way. Second of all is that they are adaptive, which means that the brain has the capacity to change and learn from experience. The third one is that there is self-organization, meaning that there is no external organizer. And the fourth is self-similarity, which basically means that the whole of the brain, or in this case, as the example, the firm, looks similar as, has a similar shape as one of its parts. So what that basically means is that what we can understand from single cell firing, we can not literally translate, but the concepts of it can be translated to larger states, such as, for example, local field potentials or EEG. But the most important characteristic of complex adaptive systems, whether it's ant colonies, economy, the internet, is the emergence. And emergence basically means that the whole is more than the sum of the components. So if we look at the picture below, well, this is not a car. This is not a functioning car. It's just all the components, all the parts of a functional car. But in order to get a functional car, we need to connect all these pieces in a very specific way. And it's the connectivity, or the way all these parts are connected, that creates the emergence of a functional car. So if we bring this more to a level of the brain, then we can have a functional module, for example, sound processing. And this functional module can reconfigurate in a disease model, which could then be the presence of constant sound, which could be phantom pain. Now, this in itself would be very easy to pick up because the structure is fundamentally different between the functional and the disease module. However, we all know that there is this game like Transformers, where with exactly the same building blocks, you get a different emergent property. So with exactly the same building blocks, but put together or functionally or structurally connected in a different way, you get a different emergent pattern, which means that you can have a disease module that looks almost exactly the same as the functional module. It's only that the connectivity between the building blocks is different. And this is important for imaging, because it means that it's not because the activity is similar within the brain that there is no problem. It can be the functional or the effective connectivity that is changed, that then creates a different emergent property, which we would call symptoms or brain disorders. So if we put this all together, then the brain can be seen as a predictive machine that uses information from the environment in order to reduce uncertainty. And what the information will be in a specific form or structure or pattern that we can recognize in the brain. And this structure or pattern or information will then reduce the information in the environment. But because of the second law of thermodynamics, that will dissipate. So the structure and form will disappear. And so therefore, the percept will disappear, and therefore the uncertainty will come back. And so what we have to have is a brain that constantly goes through circles like that. And if the adaptive or the adaptive capacity of the brain reduces, then you might have some patterns or forms that remain, and this could give rise to, for example, pain and tinnitus. Now, this information or this pattern is transmitted throughout the brain via information transmission, which we try to pick up with EEG. So the EEG in a raw state looks complex, but if we simplify it, and this is just a conceptual way of looking at EEG, is that, for example, with the Fourier analysis, we can split it up into different frequencies, and then we can propose that the lower frequency bands might be carrier waves, and the higher frequency bands might be information waves. And to put it in an extremely simplified way, you could conceive of beta 1 waves as information, as prediction waves, and then the gamma as prediction error waves. And the way the information is then transmitted is that you have an infraslow wave, on top of which is nested a carrier wave, and on top of that, ultimately the information in the form of prediction and prediction error. And the reason, and because of this nesting or this cross-frequency coupling, you do get structure within the noise, so that delivers the structural noise that we have seen to be one of the characteristics of or requirements for complex adaptive systems to arise. So from a purely theoretical point of view, it helps to look at the EEG to find both patterns, to recognize patterns, and to find the noise, so as to conceive of it as a complex adaptive system. So if we summarize this, information is basically a transient structure or pattern in the brain, especially by functional and effective connectivity, which is adaptive to the external stimuli that it gets. This information is communicated via nesting of this pattern on carrier waves. And because we perceive of pain and tinnitus or any stimulus as a unified percept, then what you need is dynamically overlapping networks of patterns that are associated with these different frequencies that ultimately all create this pink noise structure or brown noise structure that characterizes the brain. And so neuroplasticity in itself means that we change the information processing or the functional connectivity or the information transmission, the effective connectivity in the brain. So then we go to what that means is that we can conceive of neuroplasticity as a capacity of our brain or nervous system to modify its organization, and meaning both structure and function, to adjust itself to change in the environment. And then brain disorders, what we ultimately try to treat, can be simplified to maladaptive neuroplasticity, where you have an adaptive adjustment or reconfiguration of those dynamically interacting networks. And indeed, more recently, it has been proposed that most brain disorders are actually connectivity disorders, and that makes sense in that if there is a difference in connectivity, then you can go from a functional to a maladaptive disease network. And this has been proposed for reward deficiency syndromes, thalamocortical dysrhythmias, to other mental disorders, as well as eating disorders, cognitive decline, etc. So conceiving of brain disorders as connectivity disorders fits within this global picture of emergence of a complex adaptive system. Now, the neuroplasticity is what allows us then to use magnetic and electrical stimulation to modulate this, this organization. And from that point of view, neuromodulation can just be seen as the induction of neuroplastic changes via the application of electrical, magnetic, and other kinds of stimuli. Then the question is, of course, what should we target in the brain, and which stimulation design should we use? And from a practical point of view, the targeting is functional and anatomical, and the stimulation design can be conceived of as a way in order to communicate with the brain in a language that the brain itself understands. So the targeting can be done electrically, for example, by transcranial direct current stimulation, where you have an anode and a cathode, and the current goes from the anode to the cathode. Initially, it was proposed that about 50% is shunted through the skin and subcutaneous tissue, and that only 50% really transmits through the brain, whereas Buzaki's group has suggested that it might be even lower, that maybe less than 25% actually reaches the brain and 75% is shunted. More recent developments allow for greater focality by applying, by using multiple cathodes or anodes, so you can drive the current to a more focal state, which for a clinician is easy to understand, because it's ultimately a somewhat a principle reminiscent, at least, of, for example, the gamma knife, or now the ultrasound stimulation that we have. Now, what is the philosophy to treat brain disorders within this larger framework of connectivity, especially? This has already been looked at by Albert and Barabasi a while ago. So if you have a functional network that has become maladaptive, so a brain disorder network, then if you just apply random targets, what will happen is nothing, because the network will reconfigurate and basically it will continue to exist. Now, if you target some hubs, and for example, in tinnitus, this is especially the preventional hubs, then what happens is that the disease module will fall apart. And if it falls apart, the emergent property of it, whether it's pain, depression, anxiety, it doesn't really matter, will also dissolve. And this is similar to what we conceive of from a theoretical point of view, is that you have to target the disease-provoking network in order to be able to communicate and thus dissolve it. Whereas if you stimulate outside this network, nothing will happen. Of course, if you target one node, that might be like more or less like the random stimulation, and the network will not fall apart. So it makes more sense to target multiple parts, or do multifocal stimulation in order to dissolve a disease module or a disease network. Now, this can be done both by TMS and TDCS, or TRNS, or whichever by electrical or magnetic stimulation. Now, and it has been shown already a while ago that if you treat an area that is not involved in the disease network, that it will not be effective. And depending on whether and if you target the network, then it depends on whether the network is negatively correlated or anti-correlated with your target, whether it is optimal to use excitatory TMS, so high frequency TMS, or anodal TDCS. And if it is, on the other hand, if it is correlated with the network, then it might be optimal to use inhibitory TMS, or low frequency TMS or total TDCS. So, but from a practical point of view, all neuromodulation, whether this is invasive, for example, deep brain stimulation, or TMS, or TDCS, or TRNS, ultimately you have to target the disease module or the disease network. And so depending on the correlation of the target to the network, whether it's correlated or anti-correlated, you might have to adjust the way you apply the electrical current or the TMS frequency. A very practical example, here you see the default mode network. If you target the default mode network with low frequency TMS, that seems to increase the connectivity within the network. So that's good for hypoconnectivity diseases, whereas high frequency TMS might be more optimal to decrease hyperconnectivity in the brain. Now, with the development of high definition stimulation, electrical stimulation, that has dramatically changed the way we approach pathology, because we can go way more focal, as this simple comparison shows, in high definition than in conventional TDCS. But it has been shown before as well that it is actually optimal to use multisite stimulation because of this concept that you want to treat a network and not phrenologically one target in the brain, and that therefore multi-site stimulation of different cortical networks involved in a disease network makes more sense. And this and the technology for this has been developed, as we will see further down. And then the question is, of course, how do we communicate? How do we modify the functional and structural connectivity, or in which way should we talk to the brain in a language that it understands? So initially, we developed burst stimulation, which is a stimulation design that consists of basically monophasic spikes that come, well, for spinal cord stimulation and the brain at 500 hertz, and that are charge balanced at the end. And this is important because it's built on a concept that if you have tonic stimulation, for example, if this is the thalamus, this is the cortex, that a single spike will result in a response in the cortex, at least in 60% of the times, and that if you have a burst, you've got this kind of nonlinear buildup that creates, metaphorically speaking, super action potential that overrides ongoing activity, and so is a stronger activator or inhibitor of the cortex. And so if you look at it electrophysiologically in spinal cord stimulation, you have this kind of nonlinear buildup and then one big response following this burst. Whereas if you use a modified form where every spike is charge balanced, then what happens is that this is ultimately intermittent tonic stimulation, where every spike results in a small response and not in one large response. So how you design the simulation design is important because it has electrophysiological different effects. Now, when we came up with the idea, that was not based on this theoretical concept, it was based on Gaudi's idea. And in 2000, I visited the Sagrada Familia, which was still not as beautiful as it is right now. There was a sign, which unfortunately has been removed, that said that the architect of the future should construct by mimicking nature because it is a more rational, more economic and long-lasting way of building houses or cathedrals. So the concept can be translated to the brain, and if we conceive of tonic and burst firing as different languages or different ways of communication in the brain, then whatever we were using was tonic stimulation, mimicking tonic firing, and burst firing was mimicking burst stimulation was mimicking this burst firing concept. So this has been applied from a very practical point of view on the spinal cord. And what you can see is that the painfulness which is, let's say, 8 out of 10 in the pre-treatment state, is reduced to 5 out of 10 with tonic stimulation and to 3 out of 10 with burst stimulation, just suggesting that it is indeed a stronger modifier of the pain network than tonic stimulation. But more importantly, what happened is that this burst pathway, which is typical for the medial suffering pathway in the brain network, can also improve suffering in contrast to tonic stimulation. So the way you communicate to the brain and the spinal cord is important because it can modify different pathways in a differential way. Now, this brings us to noise stimulation, and there is multiple different kinds of noise, and basically white noise is purely random, meaning that the power of or the amplitude of all frequencies is the same, so it's pure chaos. Whereas in pink noise, which is the way the brain is structured and functioned, at least in waking state, there is less high frequency power than low frequency power, and in brown noise this just becomes a little steeper, and in black noise it becomes even steeper. So we could conceive of this as the same way. The brain is characterized by different oscillations, and if we do Fourier analysis and then plot them, then we get this pink noise structure. And so we can basically try to mimic this noisy activity in the brain by creating nested stimulation or just by mimicking this pink noise. So this is the pink noise stimulation design and the characteristics where you see that it does follow a slope of 1/f, or you can go to brown noise, where the slope is steeper. It's 1/f squared, and so the stimulation design looks somewhat similar. Brown noise is interesting because if you record brain activity with EEG or fMRI, you get a pink noise structure. However, if you record directly from the brain, it seems to be more brownish. So whether pink or brown will be optimal is something that still needs to be looked at. So in collaboration with Neuroelectrics, because this is designed, these are the stimulation designs that are created by Neuroelectrics. We first tested this pink noise stimulation in patients with food craving, so obese patients, where we look both at the craving and the well-being in a placebo-controlled way. It was a very small pilot study, but applying this pink waveform with high definition transcranial pink noise stimulation, targeting the anterior cingulate, where we know the craving is generated for food in food addiction, we could show that the food craving was reduced in those patients with real stimulation and was not reduced with placebo stimulation. And this was associated with a decrease of the target that we had selected by by a very simplistic approach, where we put the electrodes on the frontal and temporal targets. Now, so to bring this together, then if brain disorders are modular problems where you have different connectivities, then there is a way how we should treat hyperconnectivity and hypoconnectivity. Hyperconnectivity can be treated by applying noise to two different targets, because there's no way that you can get phase synchronization between two targets where you apply different kinds of noise, because it's just impossible to phase synchronize noise, especially if the noise is not identical in the two targets. Or you can use infraslow stimulation, so you can mimic the infraslow, where in one target you have a positive phase and simultaneously in the other you have an anti-correlated phase, and that allows you to reintroduce, at least from a theoretical point of view, the anti-correlated activity that you have within the brain networks Or you can create bursts and create pseudo randomness in those bursts, and then give a different burst in the two targets of two different networks that, for example, have become correlated in the disease state. Now, you can also treat hypoconnectivity by introducing rhythmic bursts in the concept that Hebbian concept that cells that fire together will wire together. Or you can introduce infraslow activity where the phase is the same in the two nodes that you are targeting. Or strangely enough, from a theoretical concept, you can also use noise, which sounds strange because you would use that as well for hyperconnectivity. And the reason why is that noise probably has an inverted U-curve profile, whereas if you apply too little noise, nothing happens. If you apply an optimal noise, you push the stimuli just across threshold, and therefore you get synchronized activity in both targets. And if you apply a lot of noise, then you can desynchronize. So that's what makes noise very interesting, because you ultimately then have only one parameter, which is the amplitude of the stimulation design, that might allow you to either increase or decrease the connectivity of the networks that you are targeting. So all this theoretical introduction is basically now becoming translated to pathology. So let's start with pain. So when a patient comes to you and says, I'm in pain, actually what the patient is saying, I have a certain amount of painfulness associated with a certain amount of suffering that is present during a certain amount of time. Now, the painfulness is encoded by the lateral pain pathway, which is predominantly activated by beta and A delta fibers that goes to the VPL and VPI nucleus in the thalamus, and from there to the somatosensory cortex, parietal cortex, etc. This is a pain pathway. But pain is associated with suffering, and suffering is encoded predominantly by C fibers that go to different nuclei in the thalamus, and from there to the anterior cingulate and the anterior insula. This suffering pathway is non-specific. So whether you suffer for pain, for tinnitus, for divorce, for losing your job, it's all the same medial network. And then the duration of the pain, it depends on the capacity to suppress pain. And this is initiated or started at the rostral and pre-genital part of the anterior cingulate, goes to the reticular nucleus of the thalamus, the periaqueductal gray, and from there down to the spinal cord to suppress further input of pain. Now, this is an anatomical description of how pain might be generated, but the question is, is this in agreement with reality? So we just we performed a meta-analysis of all the pain functional imaging studies. And of course, when we look at pain, there is a lot of activity associated with pain. Now, if you split this up in the painfulness or the sensory component, then it is predominantly associated with some of the sensory cortex activity, and the suffering is associated with activity changes in the anterior cingulate and the anterior insula. And pain inhibition is indeed associated with activity in the pregenital anterior cingulate, as well as the periaqueductal gray. So the anatomy fits nicely with the functional anatomy that we see in functional imaging studies. Now, pain in itself can create painfulness, and that will result in a cognitive reaction or a cognitive response, which we can measure by certain scales, such as the pain catastrophizing or the pain vigilance and awareness questionnaire. And this, for example, pain catastrophizing correlates with the cognitive and anterior superior component of the insula. But it also gives an autonomic response or a stress response, an arousal response, which in this meta-analysis is associated with the mid-cingulate and the anterior insula component. So, and the emotional response to pain, which is expressed clinically as unpleasantness, anger, fear, frustration, etc., also correlates with the anterior cingulate component. Now, if you combine this cognitive, autonomic, and emotional response, you get what we can call suffering. And if the suffering becomes chronic, patients will express as anxiety and depression, which is frequent comorbidity with pain. So suffering can therefore be described as an unpleasant experience, which is associated with cognitive, autonomic, and emotional response to the painful stimulus. And this can lead to disability, which we can measure with other questionnaires, or sleep problems, ultimately leading to functional and social impact. So if we look at that from targeting point of view, then we can try to target the pain sensation in itself. And we have done that previously by magnetic and electrical stimulation, and also by implanting electrodes on the somatosensory cortex. You can treat the suffering in itself by targeting the anterior cingulate, which we have done by implanting electrodes in the anterior cingulate for addiction, for tinnitus. Tipo Aziz has done it for pain, for OCD. So it's a target that is more general for treating suffering. And via the suffering of a component in the suffering network in the inferior parietal area, this connects to the sensory motor activity and this meta-analysis that will then result in the functional impact of the pain sensation. So what can we then do with all this information? Well, what we can do is actually, we can target those three pathways at once, just like we've seen in the work of Barabasi and Albert, and therefore hope when we treat the three pathways, we do not only treat the painfulness, but we also treat the suffering and the duration of the present pain. And this is what Neuroelectrics has provided us with as a multi, so you have to use a multi-channel device that can then target both the somatosensory cortices as well as the dorsal anterior cingulate and the pregenual anterior cingulate, meaning that we will target all the three areas together and thereby have a lot more chances of breaking up the disease module, which ultimately is the result of the interaction of multiple dynamically changing and overlapping networks, each with a different emergent property, but that ultimately lead to the unified percept of what the patients call pain, but is ultimately a combination of painfulness, suffering, and pain duration. So we will use a pink noise stimulation that is using different electrode configurations to simultaneously target these networks. We have just got ethical approval for this to try this in New Zealand on different pain populations. So in the near future, we should be able to tell you whether this should be a more performant way of targeting pain in general. So let's translate this as tinnitus or phantom sound. Phantom sound can be seen as different activity profiles in different parts of the brain. And recently we were lucky to have a collaboration with Korea to get a perfectly matched group of patients who have hearing loss, because hearing loss is the major trigger for tinnitus, with and without tinnitus. So those patients were matched for hearing loss, age, and gender, and the only difference was that one group had hearing loss with tinnitus, and the other group had hearing loss without tinnitus. When we look at the functional connectivity, it's interesting that there is a network that involves the auditory cortex, the parahippocampus, and the posterior cingulate cortex, and that defines whether somebody with hearing loss has tinnitus or not. So this allows us to use those three targets of the entire tinnitus activity profile to treat the tinnitus per se. So these are then the targets: auditory cortex, parahippocampal area, and posterior cingulate cortex. And so we can optimize the targeting, and this is what the Neuroelectrics has provided us as a target design. But sometimes it's difficult to get to deeper areas. And then if it's hard to get there directly, then you might use the functional connectivity associated with this area, as we've seen before in the studies of Fox and et al. Then you can use the functional connectivity. So basically use the cortical or surface network to get to the deeper structures, and neuroscent is used by Neuroelectrics in order to target these areas. And so then you can combine direct targeting of easier targets with indirect network targeting for deeper structures, and that will that will give us the electrode configurations that is used to simultaneously treat those three areas to treat tinnitus. The problem, however, with a lot of brain disorders is that it all depends on the imaging. It all depends on the connectivity and the imaging of the network. So in this study, we will also use pink noise, but now the pink noise is overlaid on infraslow activity, because it's the infraslow that ultimately creates the structure within the brain on which the other higher frequencies are nested. So we will, in this study, we will use a combination of direct and cortical and indirect network approaches to simultaneously target the areas with which should result ultimately in a higher chance of reducing the sensory component of the pain. So I would not be surprised that with this stimulation design, we might actually have a more a better reduction of the loudness percept than, for example, the suffering component of the pain. Now, tinnitus and pain are basically, from a brain point of view, they're the same. So as we've seen the lateral pathway in pain, medial pathway in pain, and descending pathway, well, ultimately, sound is processed in a very similar way. You have a lateral pathway, a medial pathway, and a descending pathway. And so we've seen this in a meta-analysis of pain. And if you look, there is no meta-analysis yet of tinnitus, but if you look at the different studies that have been performed, then tinnitus global activity is associated with a loudness component, a suffering component, and an inhibitory component. And so we can also target those three pathways, similarly like we do in pain. So then for the lateral pathway, we selected the somatosensory cortex, for the medial pathway, the dorsal anterior cingulate, and for the tinnitus duration, the pregenital anterior cingulate. We will take it one step, and we got ethical approval yesterday to target those three areas for treating tinnitus with a combined stimulation design. But you can push it even further. We know that ketamine, for example, can change at the cellular level, the dendritic spines, meaning the connectivity within the brain, within areas that we are interested in, the dorsal anterior cingulate, the pregenital anterior cingulate, and the auditory cortices. So basically, if we want to break up the connectivity within the tinnitus network, we could enhance electrical stimulation by simultaneously supplying ketamine. And so we will do the same approach, but ketamine enhanced using pink noise overlaid on infraslow stimulation, using this structured kind of noise, using direct or combined targeting with multifocal stimulation, selecting those electrodes based on a direct approach to the auditory cortex, and then indirect approaches to the cingulate approach. We are now also working, so we got approval for this last week as well. And so we are now also considering how we can treat suffering in general by yet applying other network approaches. But so in conclusion, this advanced multifocal transcranial stimulation is based fundamentally on the concept that the brain is a complex adaptive network, that symptoms or disorders are maladaptive network reconfigurations that might be somewhat less flexible and therefore more difficult to break. And that treatment ultimately should consist of disrupting this abnormal network connectivity, and from a theoretical percept that the symptom will dissolve. So the technique that has been proposed by others and that we will apply right now consists of targeting network hubs with new or more appropriate stimulation designs to treat specifically hyper or hypoconnectivity within the abnormal network, and that advanced network stimulation with noise and burst might be essential to obtain good results from a purely theoretical point of view. So this is ultimately a pathophysiology-driven approach that is that has been developed very recently by Neuroelectrics, and that can be tested experimentally, is what we will currently do in the first in pain and tinnitus, and we're also now working on protocols for depression and anxiety. But so the good thing is that we can really try to approach brain disorders in a rational pathophysiological way, but that intensive collaboration with companies that can provide innovative stimulation designs and multifocal stimulation is essential if we want to move away from traditional phrenological approaches to treating brain disorders, which is more a trial and error approach based on luck more than conceptual approaches. But that this should give us hopefully far superior results than we have seen up to now. So unfortunately, it took longer than expected to get ethical approval. So I hope in the future, within 9 months, to be able to give results of this new approaches that can be developed by intense collaboration with companies that are extremely good in helping us in developing not just multifocal stimulation, but also new stimulation designs. And I thank you for your attention.
Thank you very much, Dirk, for this excellent presentation. Actually, for the journey from the theory to practical application, actually is what we expect from these webinars. Actually, we had comments on the chat, and the one from Tamara actually summarized your webinar, and I can exactly say what she wrote here. This kind of webinars remind me why I love medicine and science. So this is the perfect description what you have done with this webinar. We have time for a few questions, so you can use the Q&A tool in Zoom for the questions. So I would like to ask you, Dirk, so you clearly showed that actually this phrenological approach is outdated, and when we are talking about the treatment, we should talk about abnormal circuits and networks, and even instead of using terms like hyperactivity, we should use terms of hyperconnectivity. And target networks. So the question would be how we can find those networks. And you are a neurosurgeon, probably you will know more about this. How to find our targets for tinnitus? You were talking about obviously auditory cortex, anterior posterior cingulum, and insula. But how you would define the target?
That's a very good and essential question, because ultimately we should prevent that we fall into a new phrenology where we say this connection is the only one that's important. So the way we approach it is very pragmatic. We usually take resting state EEG, but you can also or resting state fMRI, because for some pathologies like pain or tinnitus, it's easy because the pain in a tinnitus is constantly there. For other, and so we assume that for most disorders, whether that is depression or others, there is a background abnormal connectivity, and so we look at functional connectivity using phase synchronization, for example, or cross-frequency coupling between two different areas, or effective connectivity, which by using Granger causality or transfer entropy, or any measure that can look at connectivity between different parts of the brain. The problem is that you have to kind of start with an a priori hypothesis of the networks that are involved. So that's why In this case, as I've explained in pain, we started with functional activity to look at which areas might be of relevance. We tend to start with the neuroscience approach, where we look within neuroscience at activation areas in the brain. And then we select those as regions of interest to then look at connectivity, or we start with a theoretical model where we think which is involved. Once we have this hyper or hypo connectivity between different parts of a priori approach, we will then target. Another theoretical approach that is possible is to do a functional connectivity or effective connectivity analysis at a larger group level. However, that might not be optimal because what we have seen in patients is that you can have exactly the same tinnitus with hypoconnectivity or hyperconnectivity. So the emergent property with hypo or hyperconnectivity might be very similar. And so we've published two or three papers where we, for example, looked in tinnitus, where we looked at responders to implants on the auditory cortex and non-responders, and the difference was, strangely enough, not in the auditory cortex where we had thought the difference would be, but in the parahippocampal area. And in order to explain that, we looked at the functional connectivity between the parahippocampus and the auditory cortex, and the responders had hyperconnectivity. And that's because at that moment we were still using just tonic stimulation. So from a practical point of view, we just use functional imaging methodology like resting state or EEG or resting state fMRI.
Okay, thank you very much. There is a follow-up question from Stephen, actually, with a suggestion to use network analysis on patient level before, actually this was a question to you if you are doing the network analysis on the patient level.
So we have performed network analysis, but predominantly at the group level. So it would indeed be good to use that at the individual level to then have an even more individualized approach. This is good, however, in the clinical practice, not always immediately applicable. And therefore, what most of the research that we do is, and it might not be optimal, the future will have to tell, is that we try to figure out in groups what might be optimal for the group, so that, for example, if a patient then comes in with a certain kind of pain or tinnitus or depression, that we can just say, okay, use this configuration. If that fails, then it might be beneficial to individualize the treatment and to see whether indeed it might be better to change the target, because as I've just mentioned, you can have the same emergent property of hypo or hyperconnectivity within a network, reminiscent of this kind of inverted U-curve profile where not enough connections or too many connections actually give the same emergent property or the same symptom. So I fully agree that would be a better approach, but in the clinic, way more labor intense and therefore more difficult to apply in a routine fashion. But ultimately, we might have to go there.
Yeah, thank you very much. Comment from Giuseppe, actually, as a neurosurgeon myself, physicians are completely unaware of TMS and QEEG and TS, actually, for even depression. So congratulations on your bold and creative approach from US. I don't know if in New Zealand is the same. Probably you are trying to spread awareness of the TMS and neuromodulation and TTCS and different techniques that could be used.
Yes, so I'm as a neurosurgeon, ultimately the research that we do non-invasively has as goal to, in the future, be able to translate it to implants. But because the approach is more difficult to directly implant multiple electrodes and multiple targets in the brain, we start with a non-invasive approach. But we were fundamentally limited by technology because, first of all, we could not do multifocal stimulation, and then secondly, we did not have the good stimulation designs. Therefore, I think that starting non-invasively is the first step to then translate it to implants. Whether that will even be necessary is to be seen, but the question, of course, is, and that's a fundamental question that we can't respond yet, is why does this brain work or network reconfiguration occur? And if we apply non-invasive stimulation, will there be very long-lasting effects, or maybe the effects will last for a short term? And then we might have to still implant patients, but then guided by what we find in a non-invasive way, so that we can use the non-invasive responses to the stimulation as a guide to then use the same stimulation designs, but via implanted electrodes.
Okay, yeah, that's true. That's true. We have many questions. I don't know if we'll be able to answer all of them. I think there is a question from Lucas, actually, quite regarding the protocol. Thank you for doing this presentation. It's quite interesting. I work in the lab which does non-invasive brain stimulation research, and we are preparing for the project using TDCS to treat motor impairment in spinocerebral ataxia. There was a paper by Banushi utilizing a paired TDCS protocol targeting the cerebellum with the lumbar region of the spinal cord. We are planning to use this paradigm, but explore the correlation between functional motor improvements and dosage of TDCS session. Given your expertise, do you have any thoughts on this?
So we are currently actually treating in the clinic a couple of patients. We have no research protocols. So what we currently are doing is testing. We've tried everything basically before. What we are currently doing is 1 Hertz TMS on the cerebellum and 5 Hertz TMS on the motor cortex, and it's the first time we see a little bit of improvement. Whatever else we have tried before has not been beneficial. But to be honest, we have not done any studies on this. This is just clinical empirical trials. We have attempted spinal cord TDCS, both in the neck and the dorsal column for patients with camptocornia and pain, but have not been very successful. So now we will start with a PhD student to systematically try and develop a research approach to the problem. But up to now, unfortunately, it's only anecdotal and clinical evidence, and no research evidence yet.
Okay, thank you very much. Another question regarding actually FDA approved treatment for tinnitus and based on TES, based on transcranial electrical stimulation.
There is no FDA approval yet for TDCS. TMS is approved in the US for depression. So there is a lot of comorbidity between, so 80% of the patients with tinnitus have no problem. They can perfectly well live with it. 20% of them have associated depression. And then what you see is you can treat depression with TMS. TDCS, however, as far as I'm aware, has not yet been approved by the FDA for any pathology. The problem with TDCS and TRNS and all these electrical approaches is that it is unclear yet whether from a medical point of view, they should be considered as medical treatments, or whether they should be rather still considered as a for example, a food supplement, which is freely available. So this means that it has not been restricted to as a medical device and can yet be used by everybody. And I think that is a little bit worldwide the concept. So I've written a paper for an ethical journal where my position was that as long as TDCS is not reimbursed and is not considered as a medical device, it should be considered as a food supplement rather than a medical treatment, and therefore, from a theoretical perspective, should be allowed to be used by anybody who has a medical or paramedical diploma, whether that is a nursing diploma or an audiology diploma, it doesn't really matter. And so I think that from a society point of view, the society will have to come up with a decision whether to consider these stimulations as medical acts or as non-medical acts that can be offered by anybody. This might change in the future, but currently it's not FDA approved. So, but it's not forbidden either. So it's a gray zone.
Okay. Thank you very much. There's a question from Jacob. Thank you for a very stimulating talk. I wanted to ask where you see the whole brain modeling being relevant in predicting stimulation sites or type of stimulation. When thinking of brain as complex adaptive system, we might also expect indirect pathways being relevant for rebalancing the optimal healthy state. Could modeling help with that as well?
Certainly, I think modeling is a very good approach. However, we should also as a guide, not as something absolute. So the modeling can help us in better understanding the mechanisms that are involved in the pathophysiology that can then guide us to help in defining targets and then which stimulation design you have to use. But we should not, I think, like anything that we have, use in an absolute way. But certainly modeling is important to help us better understand and define the targets, and thereby thus also the stimulation design.
Okay, thank you very much. And last question, we have many, so we have to choose some regarding the mechanism of TRNS. There are different hypotheses regarding the stochastic resonance, the influence of sodium channels. So what would be the hypothesis regarding the mechanism of random noise stimulation? And if you go further with the color noise stimulation, what you proposed?
Yeah. So I don't see why I cannot. I will quickly stop sharing and I will reshare it afterwards to see if I can move the slides. So I try to have a very practical approach, and so the idea of why I am interested in noise is based currently on the concept of stochastic resonance approach. That does not mean that there is no other approach, and I'm aware that that the high frequency noise and low frequency noise has been used also to show that there is a difference. But from a simplistic point of view, if this is your subthreshold input without noise, then if there is weak noise, then what we have is we're still not crossing the threshold. Then when there is an optimal noise, then you cross the threshold, and this can then create a pattern, and this pattern can be transmitted in the brain So this, and then when we create a lot of noise, then there is no pattern anymore. So you will disrupt whatever patterns are there. So this amplitude would theoretically increase connectivity. This would theoretically decrease connectivity. And this is very good because that allows us with the same stimulation design to either increase or decrease the connectivity. How that relates to calcium channels and potassium channels, which has been suggested to be differential in high and low frequency noise, is yet unclear. One of the hypotheses is that if you nest this pink noise on infra-slow noise, which is one of the stimulation designs that we will be using in the future and that has been developed by Neuroelectrics, is that the infra-slow component is actually a calcium wave, a glial calcium wave generated by astrocytes, which creates the neurovascular coupling. So the astrocytes, depending on the activity, will create a calcium wave that is essential for burst firing in the adjacent neurons, and this burst firing is then creates the oscillations that we can pick up with EEG. So the noise that we use is based on the combination of trying to modify glial cells with the infra-slow component and then the neuronal component by the bursting in the cells that is ultimately related to the calcium, to the infra-slow component. So this is purely theoretical, but what we hope to achieve by combining the infra-slow and the pink noise is to modulate not just neuronal networks, but how these neuronal networks are controlled by astrocytes through a slow calcium wave. We have a student, PhD student, who's looking at that from a single cell level in the Petri dish to an EEG level, just to see whether this theoretical concept does make sense or not.
Okay, thank you. Thank you very much, Dirk. We are running out of time. So this was the last question. The rest of the question we'll try to answer offline. Thank you very much, Dirk, for the presentation. Thanks for all questions. I also want to thank everybody for joining us today. As mentioned before, this webinar has been recorded and will be provided by email to all participants. So I hope you will join us again for next webinars. You can find more information on the webpage neuroelectrics.com. We'll meet again in January. So Merry Christmas and Happy New Year to everyone. And once again, thank you very much. Thanks, Dirk. You're starting the day in New Zealand right now. So have a great day.
Thank you.
Take care and goodbye, everyone. Thank you very much.
Okay. Bye.
Thank you.